Thank you. Thanks for the invitation. I'm really happy to be here. I just started as faculty in January, so it's still like kind of half grad school to me, except I teach. And I was just in Baltimore last week watching the Baltimore Orioles beat the Washington Nationals, so nice job on that. Were you there? Yeah, it was a good game. So anyway, I do a lot of stuff, as kind of Hal alluded to, and I'm only going to be focusing on one topic today to keep things simple, which is on water. And that title, Under Pressure, might make more sense as I go through my talk, hopefully. It's not just like a David Bowie reference. So before I started working on this project, this is the first technical. I suppose you don't want me to walk around either, do you? I don't know if this is working. We'll see. I might have to stay here. Okay. All right, so as I was mentioning, before I started working on this project, I didn't actually know a lot about water. So water is the most common substance on Earth. Who knew that? Okay, a fair majority of you. Less than 1% of this, however, is drinkable. Most of the drinkable water supply is on the surface or in aquifers. The rest of it sort of exists in the ocean as salt water, and much of it is brackish. So interestingly, the amount of water on Earth, though, is not changing. But other things, other factors are changing. For example, the number of people who exist in the world, and weather patterns. And these sorts of things have an effect on where water supply is located. And water is highly regionalized. So as populations grow, per capita water availability is actually declining. And for the first time in world history, I think in 2007, there were more people who were living in urban centers than there were in rural areas. So as you might imagine, this is really exacerbating the problem, right? This places an enormous strain on drinkable water supplies. And I have 2 points of reference for you. The first is in Beijing. They've had a lot of trouble with sustainable water infrastructure. In 2010, water consumption rose to nearly 1 trillion gallons, which seems like a lot, and it is. But the main problem was that the water supply only supplied 576 billion gallons, right? That's quite the deficit. So as a result, their government started melting snow to provide their citizens with fresh water. But this is a problem that doesn't just affect developing regions, but also here at home, particularly along the Colorado River Basin, right in the southwest United States. They also use the most water, interestingly. So Lake Mead, for example, which supplies about 65% of Las Vegas's fresh water supply, the intake pipes, the water is supposed to go below the intake pipes in the next 5 years. So these are significant issues, and as new sources of water become more environmentally and financially costly to extract, utilities and governments are sort of changing their focus from trying to find new supplies to utilizing existing supplies more efficiently. All right? So this is an area where I think HCI research, which is what I do, can help, as well as sort of ubiquitous computing, which is another form of research that I do, and perhaps people who are working on computational linguistics as well. So in this, the sort of approach that I take is eco-feedback. This is kind of a two-pronged approach which senses and feeds back information on human behaviors in order to promote some kind of other kind of behavior, and in this case, an environmental sustainable behavior. Perhaps the most known example is the Toyota Prius. Has anybody seen this? Have you driven in a Toyota Prius? Right, it gives you instantaneous, real-time feedback on your driving behavior. And as a consequence, there's been a growing number of people who are like hypermilers, and they can squeeze out every last piece of gas mileage in their vehicles, right, just by looking and attending to that real-time visual display. And so the eco-feedback system, in my framing, has sort of 3 parts. It has you, it has this underlying sensing system, and it has feedback. And in the car, of course, those are really strongly tied together, right? They're co-located both situationally and temporally. But if we look towards the home, which is what I've been focusing on for the last 3 years, the sensing and feedback infrastructure is quite different. So water meters exist to provide data to utilities, and they're analog systems. Bills are the main ways that we get feedback on our water consumption, but you'll notice here that number's probably too small. It's an aggregate number, right? So it's actually hard for us to answer questions about where our consumption is going. So it's just this aggregate number. In fact, I'm going to turn it on you right now and ask you, what do you think are the most, let's see if we can get the top 3. most water-consuming activities in the home? Showers and baths. Washing machine. Toilet. Dishwasher. Okay, we actually did pretty well. Better than most rooms. We missed one thing, and maybe it's the way I phrased the question. What's the biggest water user? Okay, in the residential space. What's that? Outdoor. Outdoor, irrigation. And we're talking about treated water supplies, right? So stuff that you wouldn't, it's too expensive to use that for agriculture, although we do sometimes in urban centers, okay? So yeah, so outdoor use is 30%, but I think we did toilets, laundry machines, sorry that it's cut off a little bit, and then a lot of people say dishwasher for some reason, but that's only about 1% of your water footprint. Okay, and the reason why I think this disconnect exists, because I imagine most of you have used water all of your lives, right? You've relied on this sort of infrastructure all of your lives. You've probably taken showers even today, but it's hard to answer questions about how much water that shower used. And so I think this is sort of a sensing and feedback problem. I relate this to an analogy which I stole from two psychologists, Kempton and Lane. They're like, what if we went to a grocery store and there weren't prices marked on any goods? So we just were estimating the cost of things, right? And we were filling up our cart. We're like, oh, this piece of produce and this piece of meat. And we're going through. And then we go through the checkout. And then rather than getting a nice sort of itemized bill like this, Safeway's like, we'll bill you later. And you get something in the mail that looks like this, right? Total food units, 1,527. Total price, 642. So if you were a purely rational actor and you wanted to shop in an economic way, it would be difficult to do so. But that's sort of the way that we're getting sensing and feedback in the home. So we tried to change that. And in particular, we were trying to increase the granularity of information provided to occupants. So taking that number, 10,230, and breaking it down or disaggregating it into its components. And that's where we turn towards computer science and HCI, to build sort of low-cost sensing systems to sense water usage activity in the home, as well as to build real-time visualization systems to take that data, formulate it, and then visualize it for people. Okay? And the sort of prevailing way of doing this within the HCI community in the last 5 years is this has sort of caught on as it has culturally in America, this topic of sustainability. We've seen things like WaterBot at CHI 2005, Show Me, which is a water-based display, Upstream, the Waytech shower monitor, which is actually a commercial manifestation of this in New Zealand and Australia, who also suffer from water scarcity issues. So as you may have noticed, all of these are point of consumption eco-feedback displays, right? Where both the sensing, and I don't know if you could, the font there is a little light, but both the sensing and the feedback unit are co-located together, okay? And it provides real-time feedback on water usage. So this is really the prevailing and dominant method of doing sensing and feedback in water in the HCI community. And we wanted to rethink this a little bit. First, as we already saw, showers and faucets account for only 22% of water use in the average North American home. But yet that's where all of the research had gone. Okay? I don't know, maybe we need a gesture interface or something. Let's see. There we go. And the second thing is this reliance on co-located sensing and feedback together, right? That unit is one. So this is an example of it, the coolant sensor. Sorry about this. My slides are not advancing. So they're direct sensing. So what that means is you'd need to instrument every single fixture. So for example, this is what your bathroom would look like. And it actually gets slightly worse than this, because we also want information on hot and cold water, and those valves are separate, right? So that doubles the amount of sensing that you would need. So we were trying to think about doing this, but in a different sort of way. So could we build a single sensor to provide that granularity of data from a single point? And we called that HydroSense, and it's still an active research project, and it sort of builds on 20 years or so of research into disaggregation methods that kind of come out of the water utility space. 3 of those papers highlighted in orange are part of our research group. So this data, this highly granular data, provides new opportunities for eco-feedback, which I think is really exciting. And then the question is, what do we do with all this data? How do we engage people? Right? How can it possibly change behavior? And I'm not really going to focus on that too much, because I don't want to go too HCI heavy. But this is a giant design space. And if we have time, I'll kind of go through some of the visualizations that we've created based on the granularity of data provided by HydroSense. Okay? So how does HydroSense work, and how did we evaluate it? All right, so first, HydroSense is a single screw-on sensor. And it's meant to be low cost. It identifies fixture usage from that single place, and you can install it in various parts of your home. And it also provides an estimate of flow. And this is different from an ordinary meter. This is an indoor water meter, which is turbine-based. And in order to install this, you have to cut into the pipe, right? But HydroSense is different because it's relying on pressure to do its sensing. Okay? Oh, I better just not move at all. And again, this is what supplies that one number that you see in your bill. Okay, and so HydroSense, which actually started out very simply from a hardware standpoint. So we have this pressure sensor. This is an industrial pace sensor. It runs at 1,000 hertz, and it can sense from 0 to 100 psi. And then we also have just this sort of simple 3D printed case here that you can see in blue. With a 16-bit ADC, a 20 megahertz microcontroller, and then a Bluetooth radio, which actually sends it over to a laptop to do the processing. Okay? So to go any further, I have to basically go over a brief plumbing primer, which might be the first in the history of this talk series. And this is also probably my second cheesiest slide, so you can enjoy that. I thought you might like it as computer scientists. This is my first cheesy slide. But actually, and it's funny, when you search for plumbing online, you get a lot of crazy... Does anybody know who this guy is? What was that? That's awesome. I don't know how you knew that. Yes, it's Samuel Joseph Wurzelbacher. Nicely done, sir. And you know recently he was in the news. Do you know why?
Isn't he running for office?
Yes, he won the Republican nomination in the 9th Congressional District in Ohio. So there's a chance that he could be in the House representing his fine. So this is Joe the plumber. All right, so as we continue, so I don't know if you've thought about this, but we get water to our homes and to our commercial entities and the industrial enterprises in our cities through pressure. And that either happens through auxiliary pumps or gravity, right? And that comes through these supply lines, and incoming cold water comes into your home, and then you have a pressure regulator. Right? And this pressure regulator protects your pipes from high-level, big supply line spikes. Okay? So it's going to regulate the pressure. It's just kind of like a voltage regulator on a circuit. Okay? And you can go to Home Depot. You can actually measure your pressure and make sure that it's under, let's say, 80, which is kind of a standard, so that your pipes might not burst, or it can actually damage your valves if you have really high pressure. Okay? So that's like the good space and the bad space. All right? And then it plumbs and branches into various forms, and this is sort of like a canonical layout here. And the key for us is this water heater, okay? Because we're under a closed pressure system, and we're going to use pressure for HydroSense. And the key thing to think about is, as you use water, for example, if you go to your faucet and you open up the faucet, you don't have to wait for the water to propagate through your pipes. Right? It's already there, and everything is under stable equilibrium pressure. So let's go through an example. Here's HydroSense. We're just going to install it on a hose spigot, just one place in the home, and we're going to flush the toilet. And what happens is, when that valve opens, it creates a destabilization point, and you get a pressure wave. Okay? And so we're going to use that pressure wave as sort of signature. So now we're going to open up this kitchen sink cold, and again, you have this sort of high-frequency component waveform. And again, now we're going to do kitchen sink hot, and the kitchen sink hot signal is going to travel through the hot water heater, and as a result, that serves as sort of a giant capacitor on the circuit, if you will, and dampens that high frequency waveform, allowing us to distinguish between the hot and cold. All right? And I actually lied a bit, because it's slightly more complicated. To enable the single point sensing approach, that is, we can install this anywhere in the home, but just in one place, the signal goes everywhere. So the signal is propagated everywhere. All right? So that means that we could install it, and we've tried this. This is the outdoor hose spigot, which is the easiest place. Also, every hot water heater has a drain valve, which you're supposed to empty every year. I'm sure you do. It's like, what? And I was in an apartment, so I didn't have access to either of those. So we also experimented with installing below the sinks, kitchen sink and the bathroom sink. Okay, so this waveform, as I mentioned, is sort of like this nice dampened sinusoidal wave. Yep?
Do you get enough redundancy, enough diversity if you install it 2 different places that have a bit more to do?
So I go over that in this talk. But I do want to say, if at any time you have a question, I think it's much more fun for both of us if you just ask them like that. Right? So that's a great question. So that's something we evaluated, and we had high expectations. All right, so this is the open, all right? And obviously, I'm showing you a nice waveform here, okay? And this is a close and sort of inverse. You get this spike and then dampened. And you also notice that there's this pressure drop here. And this is what we can use using Poiseuille's law, which is a really old fluid dynamic law, to correlate the amount of flow with this pressure drop, okay, in a calibrated system.
Out of curiosity, what is the velocity of pressure waves in water?
I'm not sure.
Because I'm trying to think how much of a time difference you would have at 2 points.
Yes, so that is something we examined when we put the 2 sensors in as well, because we were really trying to like locate, see if we could localize different parts of the signal. I'll go over part of that. Anyway, what I'm showing you here is just a variety of signals, and I accelerated the video, obviously, as I walked around a home and opened and closed the different valves. And what I just want you to attend to here is that you can visually tell the difference, right, between different kinds of fixtures.
Sorry, we're looking at like a red line at the bottom?
Yeah, exactly. It's very,
We can turn down the lights.
yeah, it's very hard to see. Let me see if I can do that. Lights. Looks good on my screen. I see volume and mic. Oh, it's discrete. Can you guys see it a little bit better now? Yeah. So basically what was happening here is I think the bottom part was showing you like a 20-second window, and the top part was showing you like the last 7 minutes or 8 minutes. So just going around, and you can also see the different kinds of pressure drops that exist here, which might be useful as a signal feature. Okay, so this is just an example in home 1 of a toilet, a faucet, and a shower. And the signature is dependent on the fixture type, the valve type, and the valve location in the home. And so this is both good, because it allows for high discriminability, but also bad. Does anybody know why it's bad? Every system is different. Exactly. So not fun to play with. So what happens is each individual home, the plumbing system is essentially a transfer function on that signal. And so right now, the work that I'll be talking about today is per home calibrated. Right? So the hydro algorithm, this is the first one that we created. First, we just detect that a water event has occurred. So we have to do a segmentation. We classify the event as open or closed. We determine the source of the event, for example, a toilet or shower, and then we provide a flow estimate. So I'll go through this in slightly more detail. So we have your raw pressure wave. Then we just do a simple low-pass filter. And here we're looking for basically changes in the waveform that allow us to mark the open and the close. So as the waveform is sort of coming in, you can imagine you're the algorithm. We're looking for this critical change in pressure. We're going to mark that to segment it. And then we see this critical stabilization point, right? So it's a candidate to sever as well. So now we know that there's an event here, but we don't know what it is. Okay. So we look at this pressure decrease and a negative initial derivative, right? So pressure decrease corresponds with an open, so we know that it's a valve open event. And we do something very similar for the close. Look at a critical difference here and then a critical stabilization point for our segmentation. We have an automatically detected event. Look at the pressure increase and a positive initial derivative. And it's a valve close event. And I'll do that again. Okay. So now we have sort of this unclassified open event, but we don't know which fixture or valve was responsible for that. And this is a fairly actually simple, naive approach. So we have this calibrated, this template database of known signatures, and then we're just going to use matched filtering to figure out what is the best case, or what's the best match. Do you get?
Per home library?
This is per home, yeah. So matched filtering, essentially we're looking for the kind of the maximum similarity between these two signals. So for that, we have the bathroom sink closed template. Now I'm going to slide the unclassified waveform against the kitchen sink closed template. It's essentially a convolution. We're looking for maximum similarity, so in this case it wins. So this is more similar than the bathroom sink closed template. All right? And we do that on a number of different kind of signal transforms. That the primary ones were a detrended unclassified. This is essentially a low-pass filter detrended waveform, the derivative waveform, and a Kepstrom. So we look in the frequency space as well. Okay, so for an example, now we're going to calculate this against the shower. So this unclassified waveform against the shower, and we're testing similarity. Match, match, match. So we throw that into a temporary list of best matches. And we'll try it again against the toilet. In this case, one of them fails, so we throw it out. And obviously, we iterate through this algorithm until we identify an n-best candidate list. In this case, there's 3 that pass our learned thresholds. And then we just take a nearest neighbor with this derivative waveform. Yep?
You have 2 events at 4 the same.
Oh, no! Yeah, that part's hard. So superposition doesn't hold. So the question is with compound events, right? What happens to these nice, beautiful waveforms? And they get transformed in a way that makes them difficult to classify using this algorithm alone. And I'll get into that in a second. It's important. I think it's important. And I'll tell. And one of the questions we had, this is our first experiment, right? And one of the questions we had was, how often do compound events happen?
In a large apartment building, probably a lot more often.
Exactly, and depending on their plumbing design, right? And in my apartment building, that happened quite often. We had shared plumbing vertically, so the people below us and the people above us we could sense. So there's a lot of compound events. Yep.
You can also probably learn something about the human's habits.
Exactly. So, I mean, that's part of the reason why governments are kind of interested in this, because they use this, well, not for surveillance necessarily, though the NSA might be. I'd pass the NSA on the way up. But more to inform plumbing code design. So how big do your hot water pipes have to be, right? And that's a trade-off between energy efficiency and the cost of the pipes. So the governments are really interested in this sort of behavioral data as well. But we couldn't turn towards any existing data set to look at how often these compound events exist. So we couldn't necessarily run simulations. We didn't do that with this data. But we did do a follow-up study, which I'll get into in a second.
Oh, and then you could learn a prior of certain events occurring based on the previous events in the day.
Previous events or time of day.
I brush my teeth.
And so you should join our team. Because I'm just an HCI guy. I need people like you. But yeah, we looked into doing that as well, and I'll get into that a little bit later, as soon as my talk recovers here. Okay. So the first study that we performed was controlled experimentation. We had 2 or sometimes 3 people go out to 10 different field sites and run controlled trials. Okay, so that's Eric, my colleague. His name will come up again. So we did 5 per valve, okay, and it looked something like this. Here we're only going to do 1 per valve just for demonstrative purposes. So I'll go and I'll mark, I selected bathroom sink and it marked its position so that we could get ground truth data. I think my dissertation also, as a computer science dissertation, probably had the word toilet in it more than anyone else's, I would wager to guess. We also collected flow data. So this part of the experiments was really preliminary, and Eric, my colleague, has followed up on this with 2 master's students. So essentially, can we use the pressure signal to correlate it with flow? And so for that, we collected data in 4 of 10 homes using the plumbing standard, which is to take a calibrated bucket and fill it up for a certain amount of time and see what your flow rate is based on that. Okay, so we had 10 test sites. In all, we had 706 trials, 155 flow trials, and 84 total fixtures were tested. And then we used 10-fold cross-validation for our experiments. Are there any questions? Okay. So how do we...
It's just convolution. There's no dynamic time warping.
We didn't use dynamic time warping.
You may not need it in this setting.
Yeah, I mean, I was again, with my limited signal processing background, I had done some signal processing before I attacked this project, and Eric and I were talking a lot, and I thought dynamic time warping would help, and it turned out in our initial experiments that it really didn't, so we dropped it.
Yeah, I mean, it's not clear why it would necessarily help.
I mean, it might help with compound events if something was temporarily shifted. I'm not sure. But
do you also have kind of an other category that you classify things into that might catch compound events?
We don't.
This thing is sort of depend on how
So that's another good question. That's something we're really interested in. So for this first, obviously, there's a number of limitations here, right? Because we had the same set of researchers go into each home. We were likely activating the valves at the sort of same rate of flow. And so those are the questions that we also had. But we wanted to sort of look at the viability of this idea before we looked into these more sophisticated nuances. Okay. So obviously we did well here. We were happy with that. Our aggregate accuracies were above 97%. Another way of looking at this is by home on the x-axis, so y-axis classification accuracy higher is better. This is looking at by fixture, and you'll notice that showers were slightly more difficult than other things. And showers are actually challenging because there's a vast array of different kinds of designs, and also you can open up a shower by, especially in a bath shower fixture, you can divert the water, right? So you can flow out through the bath and then divert to the shower. And so that still remains a challenge for us, and I'll talk about that a little bit more later. And so for flow inference, as I mentioned, this was only in 4 homes with a preliminary data set, but actually 5 to 10% error tolerances are what you see with empirical research of analog meters out in residential sectors. So we were happy with that.
These are just accuracies in detecting which event it was.
This one is for flow. So we can separate those two things out, right? You can imagine trying to infer flow without actually trying to articulate which fixture was responsible for that flow. But these results are for fixture classifications.
Okay, so these are fixture. Because what I'm thinking is that I buy your model for fixture classification. For flow, what you don't have, which is probably critical, is that in real use, people will never go from closed to the volume they want in one step. Even with your kitchen sink or whatever, you open it and then you adjust it.
That's true.
And so on. And that's not in your model because you only have one template.
That's right.
And it goes from whatever to
So this is another question that we also had. So what happens in the real world when people might adjust? Certainly in the shower, people adjust. I would say that problem for flow, it's actually less of a problem for flow as long as you're getting those pressure decreases corresponding to the amount of water that's flowing to that fixture. But it does become a problem if let's say you have something that's half open and then you go full activation. That full activation may actually look like a new fixture being activated. Right? So that could be potentially a problem. And we wanted to look at all of that stuff. So this first study, though, was just sort of to build and evaluate the viability of this HydroSense sensor. And we're also curious about a number of questions that have sort of come up. Well, what happens if people are brushing their teeth, or they're shaving, or they're bathing in the sink, or they're paw washing, right? And so, thank you, Internet. And so we had that question as well. And the worst case is what happens if those 3 things are happening at once? Right? So we wanted to evaluate that. So we put together a second study, which we thought, I think, would take 6 months, and it took 18 months. But we wanted to study how well HydroSense could classify real-world water usage, and hopefully sort of attack some of the questions that have been arising here. Right? So before, we were using manual annotation to collect the ground truth labels. Right? But remember, we want to do real-world longitudinal deployments. So we can't necessarily have the research team, as much as maybe a few of us would like to go into homes, and have people report on their water activity, like I'm about to flush the toilet, and I'd be like, yeah, thank you, got it, right? So we can't do that. That doesn't scale. We had undergrads. I think they would have volunteered. So it really became about how do we collect the ground truth labels. And I don't know, in textual analysis, if this is hard, oftentimes, but for these sort of ubiquitous computing deployments, it's a real difficulty, right? And it's a significant engineering challenge. So the first thing that maybe even has already arisen in your minds is, well, let's just do sort of diaring, right? And let's make it easy for people, so you just put buttons on everything, and that way they can report on what they're doing. So we thought that as well, and we attempted it, and the best way to show you how well it worked is through illustration. So how many times will the hot and cold water valves be open and closed while washing these dishes? Okay, Here's the dishes. Here's the question. Here we go. Any guesses? 20? I'm either asking because it's a lot or because it's a little. But yeah, 15 or 20? Okay. Okay, so we're going to track the number down here. And we did this a few times. I won't have you watch the whole thing. I think it's at 8x. I wish it were real time. Be much easier. I'm trying to get my cursor on the screen, but it doesn't look like that's happening. Did it just restart? Ah, there's my cursor. Okay, so someone said like 20, which was really close. But for us, we were actually surprised about that, right? So 21 hot activations, only 1 cold activation. That's actually a huge burden on somebody. And remember, ground truth, we want to be as accurate as possible. So this wasn't going to scale for us. So this was our first fail. Let me just briefly go through a few of our other failed solutions because I think they're interesting. Yeah?
That doesn't actually seem like a failure. If you know that somebody's washing dishes at all, you might be able to get some of the other stuff. If you have a model of how people are likely to comply, and you say they're not going to push it all the time, but when they push it, it's probably right, and you have some model that says that the hot on and off come close together
yeah.
in some pattern, the fact that they pushed it once might be enough to be able to figure out they're washing dishes, and then you see all these other events that look similar to the first one.
Right, and in fact, I think you could even do better than that because you could have the people come back into the lab at some point, or perhaps you could send them like a weekly report, and you could have some of it labeled, and you could try to have them label other things, or you could try to have a model. But remember, the model would also induce some amount of inaccuracies in the system. So we were trying to get as accurate ground truth as possible. But I agree, there probably are ways of allowing people to use labeling to get ground truth for this.
I'm sure you're going to tell us what may have worked, but I was thinking that not something where they're required to push a button, but something that automatically senses that proximity might be the solution.
Right.
I don't know if they'll wear an RFID bracelet or something, but
right.
the sensor.
Yeah, so I mean, these our meetings were essentially like this. Like, can we use RFID? I mean, it's actually quite fun, and it's an interesting discussion. We also start to encounter Murphy's Law. So that's actually what happened with the Intel Labs shake sensors. So many of you may know that Intel had labs in 5 different areas, or 4. One of them was at University of Washington, and we often collaborated together. They had these really cool, individually addressable shake sensors. They just had coin cell batteries. They lasted for a long period of time, 4 to 5 weeks. And so we were going to put them on all the fixtures. But their error rates, they would die, and we'd have to go back. So they just weren't going to scale for us. So that was fail number 2. Then we also tried thermistors. So can anybody think about why this might not work?
On a 7.5, I'm going to put the thermistor underneath the water. We should see an increase from 7.5 volts for hot. When we do that, we get an immediate increase on 7.93, and then when we turn off the hot, we get almost a near immediate drop back down.
So the temperature is essentially changing the resistance in the circuit and allowing us to kind of measure when water might be flowing. But there was a few problems with that approach. And it's usually about hot water. So often, especially in apartment buildings, but even in our row house here in DC, if you open up the hot water, you actually have to open it for quite a long time to get actual hot water to that faucet, right? So you have sort of cold water that's sitting resident in those pipes. So but actually it's still a hot activation. And there was no way for us to distinguish that, right? And there's also the thing, if you have hot water in your faucet and you open it to cold and shut it really quickly, that'll look like a hot activation, but it's actually a cold activation. So this one didn't end up working either. We also tried this. I won't play a video of it, but we were using the piezo sensor in this Nike iPod. I did post the video because I was sharing it with my colleagues, and this is like really awesome, I think. So I'm trying to disseminate knowledge to the world. 16 dislikes. And 4,000 views. I don't think I ever like publicized it, so people must be searching for like, I don't know how they're arriving at this video. So that's like, I think that's a double fail. There's nobody that, so if you see this, maybe you can go onto YouTube and give me a like. That'd be awesome. And you could look at the comments, because the comments are really quite hilarious. So finally, our solution was custom direct sensors. But this is actually kind of, well, first, the hardware capabilities were that it had to be wireless, low power, and importantly, water resistant. And we also wanted to have, work across fixtures and appliances, detect open and closes, and we were discriminating discrete states of hot, cold, and mixed. Okay. But this is actually a hard problem, because there's so much variety in the design of fixtures. And not only that, even if we were just focused on the manually operated valves, you still have issues with single handle faucets or dual handle faucets. But we also had to come up with designs that would work with washing machines and dishwashers and other kind of like solenoid valves and so on. So we basically, yep.
Is this kind of shooting yourself in the foot since you wanted to get away from individual sensors?
I know, that's the thing. I didn't want to design this, and then I had to design it. But this isn't something that you would want to go and have somebody buy at like Home Depot and install in their houses, right? So this was certainly just, and you'll see pictures in a second, which will encourage you to never want to do this to your house. So this isn't, this is a nice solution to the problem.
But following up on the question, is the idea that you would instrument a few hundred houses and then from that you'd be able to generalize to new houses without these sensors?
We did 5. Remember, this is just to collect ground truth to validate the pressure stream. Exactly. This is for training and testing.
Right.
We need to have...
Do training for every house separately.
And,
how can you avoid installing this in a new house?
and so far we have to, right? So, or you could do it, or you could have the homeowner, I think the general principle is you have the homeowner or perhaps the utility who's paying a labor wage worker go and install the system in the house and activate N number of valves. And maybe it's less than the total N in the home, right? So it could be a subset of that. So, and they're definitely the biggest open problem, which Eric, who I showed a picture of, is trying to attack right now for his dissertation, is unsupervised learning and training. So how quickly can the system be placed in someone's home and actually accurately classify events? Okay, so we had fixture handle position sensors. So we had a Hall effect, a reed switch, and 3-axis accelerometer just to deal with the different variety of fixtures that exist in the home. And then we also had wake-up sensors. So we had these ball sensors that essentially would wake up the circuit and then have it send the handle position data. Okay, so it looked like this. This is an accelerometer, a single handle design. So you can see the accelerometer. Then we had a little 3D printed encasement, and then lots of tape. Tape is the most important. And then also, as I mentioned, we had to track appliance water usage. So for that, we used a modified kilowatt. This is actually a design that was posted on like Make or Instructables, and we just followed that essentially, and then attached our Zigbee board to it. So we had 5 homes, 5 deployment homes, and the key here is I think it's 90 water valves across these 5 homes. So we had 2 apartments and 3 homes, and this is sort of what it looks like. And this is significant time that goes into wiring up these homes just to get ground truth. These are the toilets. These are the showers. One of the homes was my advisor. And when his wife came home, obviously she was quite shocked because her house had to be like this for 5 weeks. But what made it worse is I was like, the other thing is when you're taking a shower, you can't touch the wires. And then she was really, so she was, I don't think she showered for like 5, no. But no, this was very low voltage. There wasn't a problem with that. But the other thing, so diverter valves, we had to sense when diverter valves were being used. We also looked into using thermistors. So we were getting essentially the temperature, the relative temperature of the water, so we could classify if it was a cold cycle or a hot-cold cycle. We even did things like the refrigerator, so you could get the refrigerator fixture activations. And this is why I don't intend it to be something that you would go out and do yourself. So we won't watch the whole thing, as much as we all probably like the Benny Hill theme. So it took teams of 3 to 4 about 2 days to do the instrumentation in each house. So it was a lot of work. And also with Murphy's Law, again, we had to have a real-time reporting infrastructure when sensors died, which they inevitably did, or some of them were on battery power and not on home. They were not AC powered. So remember, and all of this was just to collect the labels so that we could do these tests and validations. And getting to your point, because of this effort, we're like, well, what happens if we deploy more than one sensor, right? What else can we do? And so this is what it looks like in a home, and that's actually my apartment. So I just had them both below the bathroom sink. And then we had a laptop which would aggregate all of this data and then push it up to a web server. So I'll just play a quick movie of what this looks like. So I flush the toilet, and that's using a reed switch. And the blue, so you have your pressure wave here, right? So the red is hot water, and the blue is cold water. Okay? So a lot of engineering here. Python web backend, we get emails when sensors died and so on, and then a lot of analysis infrastructure. But the key is, even there, we weren't done because our ground truth sensors didn't give us perfect data. They didn't tell us, for example, they told us when a toilet flush event began, but not when it ended. So we hired undergrads to go over using a tool to actually complete the annotation. So this looked like this. So you have your pressure stream here. You have your ground truth data here. And then our tool would sort of assist an annotator in semi-automatically labeling things. You see that? So we'd get the open and the close. And here's a sort of zoomed out example. So someone had to review all of these annotations. We had 3 people do that. All right. So then, finally, we had this sort of cleaned data set over about 5 weeks in each house. And a total number of events of about 95.9, which we thought was kind of high. So this is the average number of events per day in each home. These are activations. And so home 3, you'll notice there's a big spike. But actually, it's because there was 4 people living there. So there was about 35 to 46 water events per day in each house. But what was more surprising about this is, remember, we were instrumenting so we could learn about both hot and cold water. And there's a significant amount of hot water usage. So in one apartment, 75% of all activations had some hot water. So it was much higher than we thought there was going to be. And in terms of fixture activity frequency, it essentially follows a power law distribution. So if you were really interested not in sustainability necessarily, but in building activity-aware computing, like for elder care assistance in the house, you'd want to at least be able to detect the top, say, 5 things. These might not correspond to the most water usage, but these are the most activations, right?
Yeah, that was my question. If you reweighted this, presumably bathroom, shower at the right end.
Bath wouldn't be, just because none of our homes really use the bath that often. One house, actually, my advisor's house, every single day, and this speaks to the repeatability of human behavior, they would open up about the same time their bath for about 2 minutes. Then they would switch it off and they would go to their shower. They were 2 separate fixtures. Does anybody know why they did that? They go open the bath for 2 minutes and then go and take a shower. Get the hot water. Because you have like a bath faucet just pours the water out, maybe at 5 gallons per minute. So it's trying to get the water into the pipes, the hot water into the pipes.
But the question there was, would the graph look very different?
It would.
If you weighted by
Yes, yes. So that was purely activations. Yes, yes, it would. Okay. And we could have done our analysis that way as well, but we did it at the event level and not at the flow level. Yep.
Let me just go back for a second.
Yep.
These are compounding both hot and cold water.
This is at the fixture level, not at the valve level.
Right. I'm wondering whether, because one slide earlier you had said there was much more hot water faucet activity.
Yeah.
I'm wondering whether that's because we tend to intrinsically regulate hot water much more carefully. I don't mind the cold water tap running for a few extra seconds between things. But if it's hot water, I might stop it because otherwise it's too hot.
Right.
So in other words, the total volume flow, I suspect, will be much more for the cold water.
Yeah. And I don't remember if we looked into that. But yeah, your suspicions might be right. So for compound events, which is the big question, what do you guys think? How often does this happen?
How large is the house?
No, I was going to say, how many people in the house?
Exactly. So it's a function of how many people live in the house as well as how often they are co-located together. But one of the biggest reasons why there are compound events actually just deal with the individual. Okay, so overall we had 22%, which was higher than we were expecting, of all the water events were compound. So what?
You wash your hands while the toilet's flushing.
There it is. So you, even as an individual, are creating compound events of your home, hopefully. And again, I think this is a great, if you guys are, some of you are grad students, you should do deployments of your advisors' homes about hygienic practices, because you might be able to observe certain behaviors that do or do not occur. But yeah, so 41.8% of all bathroom sink events were compound, right, for that exact reason, hopefully. So let's look at a compound event really quickly. So this is your bathroom sink. This is an isolated event. And again, we have that nice crisp waveform. Okay, and here we have a compound event. So we have this toilet flush activation. Okay, and so you can tell that because water is actually flowing in this piping system, you're now having a sort of dampened result on that waveform. And does that template approach actually work? It depends on what kind of deformation actually exists. Maybe, maybe not. So the nice thing is the frequency components still are okay here, and your flow rates you can still sort of calculate. Okay. So that could be 2 points of, oh, my machine's not advancing again. And this came up already, okay? That there's so many features in our feature space that we weren't utilizing with the template matching approach. We were focusing a lot on the signal and not on the human behavior. Not on when this was occurring, not on the previous events, on the priors, not on certain sequence strings which occur more often, or the duration of water activity. I mean, certainly faucet activity is going to be less than toilets, which is going to be less than showers. So all of this data we weren't taking advantage of, and there's a lot of other features that we then explored in our second algorithm. So I have about 5 minutes. I'm going to go over this updated algorithm, the results, and then I'll skim over some of the feedback visualizations and take questions. Okay, so we can end on time. Because there's questions at 10:30 or 11:30, right? Okay. So our new algorithm actually was informed by, actually straight out of a textbook, I believe, by speech recognition. So here, instead of trying to classify vocal utterances, we're classifying these valve activations. And we're taking into account sequences, right, and priors. And we do that, so we have the signal, which is basically the first algorithm that I presented, more or less, and then behavioral characteristics. And we did that with a Bayesian probabilistic approach. Here's Bayes' theorem. I think you're probably all familiar with it. This is the most likely valve sequence. So now we're modeling valve sequences rather than individual valve events, and this gives us a lot more power. So our conditional probability term is this match filtering, essentially. We also looked at stabilized pressure drop as a feature. Okay. And then the transition probabilities. So we can finally capture the fact that if we see a toilet flush, there's more likely going to be a faucet activation after that. And then there's also a grammar, so certain things can't happen. And before, it was possible for us to classify something that doesn't actually make any sense. We could say a kitchen sink open, followed by a bathroom sink close. So we actually created a soft grammar to try to rule out some of these possibilities, or de-weight, de-emphasize some of these possibilities. And then also things like we did pairing. And again, we didn't do that before, and without pairing, you don't get things like water usage duration. And that's important to get passed for compound events. Okay, so here is the classification results. Again, y-axis is better, or is classification accuracy, so higher is better. And this is essentially the same graph that I showed you before. We're at 98, 99%. Okay, so we're not, even with our new algorithm, we're not doing as well, right? We're at 75%. And that just speaks to the difficulty of real-world data. There's a lot of characteristics here that we didn't foresee when we were originally putting together our controlled experiments. So this is at the valve level. This is being able to discriminate hot and cold, as well as the fixture. But if you go up a level to the fixture, then we do slightly better, but it's a slightly easier space, because you're reducing the number of things you can classify. And then here's at the fixture category level. Okay, so the fixture level would be like kitchen sink, upstairs bathroom faucet, downstairs toilet. But at the fixture category level, you'd be like all showers are grouped together. Okay, all sinks are grouped together, all toilets are grouped together. So we do better there. Now the question of, do we get a better success with the second sensor?
Actually, before you go on, this other valve in the same fixture? In other words, this is not a new result, is it? Or is it that the classifier has fewer categories?
The classifier has fewer categories.
Oh, I see.
Yeah.
I thought that you were just...
We trained it. We actually did 3 different kinds of experiments.
Okay. But do you know if you looked at that result, the first one, but you scored yourself benevolently,
Right.
would you still get 89 or would it be worse or better?
Yeah, that's a good question. I can't recall if we did that. But we created confusion matrices for all of these that I have saved too, so it'd be something we could investigate. Yeah?
So going back to the motivation of this, how much information do you need to provide a user? Like which of these bars will the user need to
Right.
adjust their behavior?
And that's something I talk about in my dissertation as well. And it's I did a lot of formative work. I met with Seattle Public Utilities multiple times and spoke with them about their billing practices and the kind of information that residents need to sort of understand their practices. And I also did a lot of formative work through interviews and surveys myself, which I didn't really present to you today. So it's a great question. I would say it's still sort of unanswered. But I think the key is to, if we had a system like this, to visualize and recommend personal data for you, right? So if you have a certain kind of practice of watering your lawn, say at 11 a.m. or 3 p.m., which is one of the worst, most inefficient times to water because of evaporation, we can explain that to you, and so you can make small behavioral changes for the most impact. We don't want to worry about, that sort of bottom 80%. We would just focus on the top 20%.
Do you think about changing the box so they meet the frequency signature? So we mechanically changing them so they would characteristic of each bulb?
So try to actually model the...
Like a sound of different whistle from the box. I mean, something.
Oh, to actually actuate something, to actually inject a signal into...
Changing mechanically the shape of the box. So
Right.
Install different valves in the kitchen and the bathroom. So that
Right. I mean, that's possible. So we actually ended up licensing this work, and we were talking to people and pitching it. A lot of times they were really interested in, can you detect which kind of valve people are using? So we can feed that data back to the manufacturers and even try to do some quality control about valve breakdown over time.
You could make the sound unique for each bulb, so you can identify all of them in unique.
And I think that probably in the future, let's say if we fast forward 100 years, it's likely that we will have sensors nearly everywhere, and that might be an approach, but we were really trying to get around of modifying infrastructure.
This is a very simple modification. Maybe just change slightly the shape of it.
It's possible, but it still would require you to go into...
Yeah, sure, of course, but
Yeah.
it's simple enough that maybe.
Right. I mean, I think there are certain modifications one could make so that the problem is easier. Yeah. But yeah, we wanted something that would be scalable and sort of easy to install. Here's with our second sensor. So we did marginally better. I'm not sure. It would depend on the context of use, whether or not this was worth the money to actually have these 2 sensors. And when we licensed it, they were actually thinking they could manufacture this for very, very cheap. Our system, which I showed you with the ADC and the microcontroller and the industrial pressure sensor, was like $300. So, to make this really economically viable, you'd want something that's like $15 cost. So you could retail it for more. I don't know, like Best Buy has their margins, Okay, so in terms of our error rates, we have our old algorithm here, and now lower is better. Sorry for the switch there, but lower is better. And then, let's see, the collisions, which are actually, and I didn't really speak about this, but collisions are when 2 valve activations happen very, very close together in time, versus a compound is when you just have water flowing and then a valve activated. All right. So that's our old algorithm, but with our new algorithms, we did appreciably better. And with dual sensors, even better there. So there are some benefits of having 2 sensors installed. In terms of training, we looked at the days of training data. This is contiguous days of training data, and you do get it planes out around 80%. And I can't remember if this is at the fixture level or fixture category. But here's zooming in, and standard error is the error bars there. So, I think the idea would be if you shipped this, you'd either have the utility sort of subsidize this and try to install it, or you'd have an application that walks people to certain valves and has them flush a toilet and then mark it on the app to sort of train the system. But I think this is the biggest unsolved part. And looking at corresponding signals across homes is a big part of making this sort of viable for anything that's ubiquitous computing that requires training. Right? People are used to doing some training. When you get to Connect, you do some training. But it can't be substantial. It's got to be really lightweight. And I think I'll skip out on doing the visualizations. But so the second piece of my dissertation was really focused on what can we do with this data, how to best visualize it, coming up with different ideas around gamification and persuasive design to give people a better understanding of their water usage behaviors in the home. So we had a lot of questions during the talk, but I'd totally be welcome to taking them as well now.
I have more questions. I'm just sitting on it.
If not, I can show you some of the visualizations.
I was wondering, so among the early adopter community, the people that are already installing these kinds of like custom things in their own houses, do you think this would be immediately deployable, essentially they could train it themselves and they'd be willing to put the effort in? Or is it something that's too much work even for an early adopter?
I would say this is probably not sellable until you lower the training costs. We have to do more analysis on the largest amount of training. I mean, one approach could be like, look, just have people train the things that we know are heavy water consumers. So get a signature of the irrigation system, get a signature of the laundry machine and the toilets, and then try to do unsupervised learning for the other events. I really think that a system like this probably needs to go into the cloud, be instantly installed, no training, go into the cloud, try to do signature matches. If there's some failure, then try to do an approach with event labeling over time, where something pops up on their iPhone or they get an email and you can label for motivated users. But there's a number of these approaches that are coming onto the market through different startups in the energy space and gas and water, and a lot of them have this problem for single point inference approaches. So yeah.
So have you tried training on the easy to collect data like you did in the first experiment, but evaluating against the hard to collect, like the real ground truth?
Oh, for training, yeah. And actually, when we did our instrumentations, we actually did similar controlled experiments, but we never ended up running that. So you're saying use controlled data to train the system?
Well, so I don't want to instrument my house with, like a billion
Right.
sensors in order to train, but I would be willing to do this thing where I walk around and flush toilets and
Right,
stuff
right.
like that, and maybe hit buttons on my iPhone. So I guess my question is, if the per home data that you got was sort of this course level, not very nice data, but then you were to evaluate it against the ground truth which you collected in this fancy way, like how much disparity do you have between those?
Mm-hmm. Yeah, and I mean, I would never imagine that anyone would probably install all of those sensors. That was purely for a research validation approach. And even with what we did, we only did 5 homes, which I think for a lot of machine learning people, it's like, well, that's still just kind of a case study, right? And so it is, but it just was such a huge investment of time and engineering. And now that I'm a professor, I really have to think about that from a student's perspective and how much they can sort of spend doing these sorts of experiments. So I think pairing with, like we talked to NREL and a variety of other government agencies about trying to actually get up to 100, right? So that your N is higher so that you can do some more sophisticated experiments on the data. And also look for correspondence between homes, which I think is, there probably is going to be something like that. For some features in the feature space, for example, duration, right, there are things that are going to be consistent across homes to some extent. Those high frequency aspects on the pressure waveform, probably not. Other things. Yes?
For the grammar, what kind of model did you use? Statistical?
We used, I mean, it was a trained grammar. It was statistical. Like I mentioned, it was a soft grammar. And I can't remember exactly the way we did it, but it's in the paper, and I can forward that to you if you'd like.
It sounded like it was stuff like open and close events on the same plus after operative.
That's right. There was 4 rules, and I can't remember them off the top of my head. But one of them was an open must be followed by a close. You couldn't have a close without an open. Yeah.
So you have
So it was just four simple rules, and I can't really remember. And then it wasn't hard, so we never kicked anything out of being relevant, but we just weighted it. And that's another opportunity for future work, which is coming up with weights for each one of those probabilities. So there are certain things that are likely more important, that we just didn't examine yet. But there's a number of grad students at UW who are still sort of looking at this. Yeah.
So you're certainly doing the right thing to be treating this as a noisy channel problem. And the notion of modeling human behavior is certainly a way to help with unsupervised learning. So all that stuff is great. There is one move that looks like you haven't made yet, which is to do more than just find the single best explanation. So you're finding this V hat, which is the most likely sequence. But if your goal is to, for example, give somebody a better itemized receipt of where they spent their water, then you want to average over all of the possible sequences, which you can do. It's computationally slightly more expensive, but still completely doable for what you're doing.
Are you talking about like having a trellis or something, or?
Well, right. So you have a trellis which gives you the posterior probabilities for all of your reconstructions of event sequences.
Right.
And if you want to be able to give them means and variances, if you like, on how much water they spend on different activities.
Right.
By considering the entire set of reconstructions.
Right. Well, and I think that speaks to the tolerance of human behavior in terms of perceiving data as accurate. So people aren't used to seeing variance in their water bills. Right. I mean,
it's not the variance of their use; it's the variance of your estimate.
Right. I understand that.
It's an HCI problem, 100%.
Totally.
But my real question, I mean, if you were just dealing with me, that's enough. The point is that you're measuring for classification accuracy, and
it's a good point.
High volume events wrong, or if you mismatch a beginning and an end, so that you think that an event that actually took 1 second actually took hours. Because you put the close event way down there instead of over here.
Right.
So that's going to give you a big error on your eventual water bill.
Right.
That you're giving people. So this is why I was asking whether measuring by flow rather than events would change the graph a lot.
Right. Yeah, it's a good point. And I do think it's a sort of an active area of research of visualizing variance for people in an understandable way as we move from discrete input in HCI to more probabilistic input with our everyday interfaces like gesture-based interfaces or like connect-based interfaces. Yep.
Did you actually check what ways of interacting with the actual data, like in real time or whatever, would actually reduce water consumption, like alerts if you're going over?
So like a behavioral trial? So we haven't done that yet, but I've got the visualizations, and now I have some students working more actively on the visualizations. So there's a number of different ways that we played around with visualizing them. So these are sort of design probes, and we had a different design set which were far less complex. They were just bar graph-based things. And so these were sort of static representations, or I coded some of them up in C#, and now we're doing them in JavaScript with a MySQL backend, which will allow us to do that exact kind of thing. So kind of an A/B test, if you will, a conditional behavioral trial. But even that is difficult to do because we're likely only going to be maybe working on 8 to 16 homes. And so it's just, we're not going to have a lot of statistical power.
Could you just explain how the fish tank?
Yeah, I mean, these are like, this is the HCI part, which I love, and we kind of ran out of time, but I would love to talk to you guys about them. I'll just show you the fish tank one and maybe rain flow, and let me just forward through that. So some of these are what I would call very pragmatic displays. Other ones are narrative. You may have heard of gamification, which is taking data and trying to use game design principles to make it engaging or possibly persuasive. And I've done a lot of work in this space. So UB Fit is for personal fitness, and UB Green is for sustainable transit, which is also in my dissertation. So here we're taking narrative and sort of gamification and applying it to an aquarium, an in-home kind of aquarium. So we have this ambient display in your house, and here the narrative is you have Frank the fish, and he's sort of lonely, but if you meet your water-saving goal, then Frank the fish might meet his mate, and you meet, then they have children because you've reached another goal, and so on. And this one I actually did do in C#. And it was on a Windows 7 tablet, and so you could actually interact with it, and different fish had personalities and so on. So this is one that we're actually now converting over to JavaScript, so we actually do these deployments on Galaxy tablets, if Apple lets them. Yeah, so we did online surveys of 750 people looking at some of these designs, as well as in-home interviews, where we brought in tablets with picture frames around them, so they didn't look like computers, and we showed people these things. So they didn't look like traditional computers. And so this one, especially we were targeting families, this one was incredibly provocative, as you might imagine. So families really liked it. But there was a problem that came up. They thought it would be a tremendous education tool to teach their kids about a green or conservation ethic, but they were concerned that the gamification might be a little too strong, that it would actually start to dissuade their children from hygienic practices, right? Like they'd have yet another argument to say they don't want to take a bath. Because the way we'd explain it is, that they themselves could set whatever water savings goal they want, right? This wouldn't necessarily be on the aggregate level. You could just set a water savings goal of wanting to save water in your shower or irrigation. You could target whatever you want with HydroSense as the back end. So that kind of arose in our interviews. So yeah, we played with this visualization space from being very kind of scientific, engineering-oriented presentations of information all the way out to this, which is very approachable and kind of fun and playful. So thank you for asking about one of the visualizations.
You said you were going to show us a breakfall.
Okay, I'll show you that one. This one is my favorite. It didn't test super well. So essentially, a lot of the visualizations that we tried were bar graph based, because they're like USA Today even has bar graphs, right? So they're very understandable. So this one was essentially taking a bar graph but making it a little bit more playful and fun. So at the bottom you have a container, which is essentially a bar graph, okay, and it fills up as you use water. And I coded this one up as well in C#. So we would take the data that we had collected from the ground truth deployments and then feed that into our visualization framework so that I could experiment with how they would look. So I'm going to pull the time to then feed the data into the visualization. So you can see the time up there is going up. That's because I'm artificially increasing it so that it's pulling the data from the database. And as you use water, as you might expect, the flow rates come out of the different fixtures. And these, we have dual encoding. So the width of the flow rate corresponds to the amount used that day. Not in the moment, but that day. Okay? And now we're going to get to the point which didn't test very well, which is this notion of moral judgment. Container overflowing, right? Suddenly we have technology mediating what's right and wrong, and some people really react negatively to that. But the reason I did it was actually a very pragmatic one. I wanted to keep all my y-axes the same. And the only way to do that was to come up with an overflow mechanism, right? But so I've got to come back. And anyway, you can interact with it. Maybe you saw it's a very simple particle system, so you can interact with it with your finger and so.
Don't use the toilet.
Yeah. Don't ever use the toilet, and actually don't color the toilet with yellow or brown. Yeah, so I'm really interested in then actually doing some field deployments, because so far we've just done formative evaluations with interviews and bringing these displays into people's homes for short periods of time, so not for long periods. So that's kind of the next step with this. Yeah.
Have you considered at all, with all this data being generated and put on the cloud, what sort of privacy issues this might create? So only someone can access, what exactly you want.
So I think that's a it's a fantastic question. It's something I'm very curious about. Surprisingly, in HCI, it's not that sexy of a question, but I think it's a very relevant and pertinent one, especially in terms of the viability of this technology in the future. It's likely, given the smart grid, which perhaps you guys have read about. But utilities are gaining more and more data on us. And there's ways of actually kind of inferring different things from that data. This is far more advanced than what the smart grid has access to, right? So it's a great question. Part of it is privacy from the outside of our home, externally, what could people learn about us, as well as within the home. And we evaluated both of those things through our interviews and through our survey. So towards the first one, do people have a concern about sharing their anonymous water usage data at the fixture level with other people? They tend to say no. Okay? I think it was something like 80% of people are totally open to sharing their data as long as it's anonymous at the fixture level. Of course, this is self-report, and we might get a different response if there was some kind of news item that came out about how people were able to figure out when people got out of bed in the morning or something. But in general, there wasn't a problem with that. Within home, though, it totally becomes a much more nuanced question. And surprisingly, this seemed far more threatening to people. Okay? Which is to say that these eco-feedback systems aren't visualizing consumption activity, they're visualizing a record of activity in the home. So, for example, let's imagine that you had this display, and rather than rain flow, which you can't tell when activities occurred in time, I'm showing you just a time graph. So you can see spikes of water activity, and it's disaggregated, so you can see it per fixture. And you notice that your 11-year-old, the bathroom that they use was being used at like 1 p.m. that day, and it was a school day. Right? So you get home from work, and maybe you even see it because you can log in and see this data in real time from your work. And then you get home, and you go and you're like, what were you doing? And it turns out he was skipping school. So there's actually a lot of stuff that we even observed in our ground truth data collection that you can learn about people. We had in another house, we could totally tell when they were using their coffee maker, essentially when people got in and out of bed. And we started doing that. And I think the cool part about it, so that's kind of the negative pessimistic view, which I totally appreciate, and there's got to be ways of visualizing that or at least abstracting visual detail. But another part that I think is really cool is, what if we could use this? This is sort of what the frames looked like here. But another part is, get there. Right? So this is 3 homes. You could actually see immediately that there's differences. So just look at these. These are pressure waves, but we're way zoomed out, so I don't imagine you can see that. But you can see the tick marks of the annotations. And so the first thing to notice is that, the bottom house is far more active during the day. This is 4 undergrads. The other 2 houses are 9 to 5ers, essentially. Right? And you can see when people go to bed and when they get up. And so then the question is, how routine is this behavior? How predictable is it? And if it is predictable, how can we use resource sensing in the home to provide support for elder care for aging in place? So I have a grandma now who has Alzheimer's, and my grandfather had to take care of her for a long time, and now she's in a home. But to try to extend one's life to live, somewhat independently in their house through this system that could, say, alert you when grandma hasn't gone in and used the kitchen and it's 10 a.m. and she usually does by 8:30 that day, right? So I think that there's an opportunity sort of in the health space, as well as looking at correlations between mental depreciation and hygiene. So those things are correlated. People might forget to flush the toilet or shower. So thank you. I think there's definitely an NSF proposal somewhere in the privacy and smart grid space. So I'm interested in it. Other things?
Maybe this is a question for the audience, and let me see if I can get some people to participate and answer. What kind of information do you want from them? It's nice for John to say, I can give you all this information, but what would you want? How would you use it?
You find out whether your sanctimonious spouse is taking one shower.
Exactly. 3 showers a day.
That's not me. You can't or anything about my family.
So in a slightly different direction than water consumption, it'd be interesting if you could use this system to detect early on when you have plumbing problems. Because usually we wait until there's a disaster, and then it's very expensive to fix, but maybe early on you can detect some sort of change.
Yeah, that's why State Farm gave us like $250K a couple of years ago to look at that exact thing. There's a lot of things in our houses in which are sort of really expensive if they, fires or water damage can be incredibly expensive to fix. But we don't really think about. So there's definitely, one of the things we noticed in our ground truth data set too is that we could detect leaky toilets just by some of the repetitive behaviors that we're seeing. And so I think there is a space there as well in automatically detecting sort of the health of the resources in the home. And you can look at this beyond that. So Froehlich Patel was my co-advisor, and at Georgia Tech, his PhD was doing electricity usage desegregation. Okay, so a lot of the similar approaches from a single point. And so you can look at this more broadly about having these kind of sensors in your house and what that might look like and what we could do with the data. And I think ultimately what we're going to go to is not just this kind of visualization system. You might have a smart display that tells you the health of your house, the security system, all these things. I truly believe that that will occur. But that the system, people are going to be far less interested in these visualizations. They'll want the computer to do the computation, the analytics to tell you what you can do, right? And I think that's the true power. It's kind of Mint. If you log into Mint, you can dig in and dive in if you want. But it also says, hey, look, it doesn't look like you're getting that 3% return. And here's a bank account that will offer that or whatever by just mining your own data. And I think that's probably what resources is going to be like. Because people just don't want to spend time thinking about it. Yeah. Yeah.
That would probably be very useful for you.
Do you know how much the average gallon of water costs in the U.S.? It's less than a cent. Yeah, it's a quarter of a cent. So it's for electricity that often makes bringing in costs, and we did that. If I had time to show visualizations, we did emphasize costs in some of them, but they're oftentimes so low. But at the same time, even with costs in Seattle, which is what we were using for our visualizations, you could see that, showers cost me on average $25 a month. You could actually get this crystal clear, something that you would have never thought of before. It's like, watering my lawn costs $90 a month? I never thought of that. So it's kind of interesting to think about that. Yeah?
So I wonder if you can actually use this kind of information to do some sort of like a, what's the word, like study the behavior of people. For example, if you have a meter on every block, it can infer how many people are unemployed or how many kids are on the block.
Yeah.
So to do a sensor.
You guys should talk. It's exactly what you don't want to have happen, right?
But no, I mean, this kind of information can be useful for government and for
So, yeah.
not to track the individual, but say, these blockers, the enforcement rate has gone up by so much.
Well, and also to set water efficiency standards. I mean, one of the most substantial water efficiency standards in the U.S. did not come out of water legislation. It came out of energy legislation. So there's really a strong importance of actually saying, well, having data that represents what are the big water footprint contributors in a house, so you can then argue to your legislation about new laws that should be passed for fixture efficiencies.
The word I was looking for was census, so to do like a census based on just the water consumption.
Did you guys see this like 3 years ago? There was a graph in Canada. I think it was during the Olympics, maybe the Winter Olympics. And it was U.S. versus Canada in the final game. And there was, there's 3 periods in hockey. And the water utility in, I think, like Ottawa or something, released this graph of their pressure rates. And what you see is it goes, and those were exactly corresponding to when they had commercial breaks and the period breaks in the game. So sort of doing like this high-level modeling. So it's interesting to see how much like footprints, digital footprints sort of exist when we interact with the new world, right? There's footprints everywhere. Well, this was...
How many people are watching the game, right?
Yeah, well, I mean, all of Canada is probably... My wife's Canadian. She's like rejoicing in the streets. I think they even had riots, didn't they, or something? I don't know. Very politely. With like soda and water. I don't know. Are there other things? So a lot of this stuff is on my webpage too, and you can go, you can Google me, and I'd love to chat if you have other ideas. I am looking for collaborators. I don't know how closely this overlaps with anything that you guys do, but hopefully it was still interesting. Yeah, did you have a question?
I don't mind.
Okay.
Hey, John, we'll be here for lunch, so you can.
Yeah.
One more thing, housekeeping announcement. I think your original schedule said we'll start back at 1:30. We'll start a little earlier. Like an hour is probably enough for lunch, so we'll start at 1 o'clock. And we'll have the team progress reports and updates so that we can call them. And that way, John will get to hear a little bit about what you guys do. So,
Team Penn, Team Domain. I saw that.
go Terps.
Yeah, well, I didn't see there wasn't a Team Terps up there, right? So, fear the turtle.
So let's thank our speaker.
Yeah, thank you.